I'm legally obligated as a math teacher, I've told you this before, we just can't leave things easy. We have to make them more difficult and more complicated. Good news is this is as difficult and complicated as they're going to get. We're talking about use substitution. This is, I believe, the final section in the chapter. I don't have my textbook in here. But use substitution is going to be the thing that you don't like about this part of calculus, but it's also as difficult as things get as far as the mechanics. Until next semester, you're going to learn some other methods of integration that are a lot more complicated than use substitution. But for us, this is going to be it. This is an expression that we want to evaluate, indefinite integral. And it's more complicated than just number times letter to a power. And it's not trigonometry. And it can't be simplified to a polynomial, to coefficient variable to a power. So we're going to need a new trick to deal with this. And of course, it's going to be use substitution. I already mentioned that, but you don't know what use substitution is yet. What makes this something we can't deal with is the fact that we have something more complicated than a single letter in here. If this was just the square root of x, we could rewrite it as x to the 1/2 power, we'd be good to go. But we don't, we got something more complicated. And how we're going to deal with that is we're going to replace this with one thing. We're going to replace 3t minus 5 with u. We're going to let u represent that so that we can write this as the integral of the square root of u. Right? That's u to the 1/2 power that we can deal with. But we can't do that dt, right? The variable in our expression needs to match with the variable in our d. It's not 100% true. You'll learn d can represent other stuff in the future. But we need a du here instead of a dt here. So what we're going to do is we're going to do the derivative of both sides here. We're going to do the derivative of 3t is 3 dt. Derivative of constant is nothing. And this is going to be du here. So we're going to do the derivative of both sides, kind of like that implicit differentiation, right, where we keep the dx's and the dy's. We'll keep our dt and our du. The thing we want to replace is dt. So if we solve this for dt by dividing both sides by 3, we get dt is equal to du over 3. And that we can do a direct substitution. We need to get du divided by 3. Now we've converted this thing completely. We started with everything in terms of t. Now we have everything in terms of u, only u's, no t's. Now we can proceed. So replace this thing with u, then replace the dt with something in terms of du, then perform the integration, or well, actually, what I would do first is rewrite this as 1/3 the integral u to the 1/2 power du. Right. That way we don't have to worry about this constant here, and we've got our u to a power. Our integral then is going to be 1/3. Keep the constant out in front. We're going to get u to the 3/2 divided by 3/2, or multiplied by 2/3, plus c. Now, we're obviously not done because we had a problem in terms of t. We didn't have a problem with u's in it, so our solution can't have u's in it either, but the rest is really easy. 1/3 times 2/3 is going to be 2/9. And u, we know, represents 3t minus 5. So we're just going to replace the u with the 3t minus 5 to the 3/2 power plus c. And we're done with that. Now, if you want to check this, you could do the derivative of this, and you would end up with this after you simplified. In the process, sorry, my laptop was open, glaring on the screen. In the process of doing this, you would have to use the chain rule, right? You'd multiply by 3/2, new power would be 1/2, and then you'd have to multiply by the derivative of what's inside. Use substitution is the backwards chain rule. We don't have a backwards product rule or quotient rule. We do have a backwards chain rule. You'll learn backwards product and quotient rule next semester. Let's do another one of these. Wish I bought the eraser before the world went to hell. I bought the marker boards and markers, forgot the eraser. Got the integral of x times x squared minus 3 to the 5th power dx. We could, if we really wanted to, we could multiply all of this out and get it in a polynomial form, but I don't want to do that with a 5th power. That's going to be really tedious. So what we're going to do is say this needs to be something simple to the 5th power. I'm going to use u to represent x squared minus 3. We're going to find du. Du equals 2x dx. A little bit like chain rule there, a little bit like implicit differentiation. And then we're going to do dx equals du over 2x. Right? Dividing both sides by 2x gives us dx. We need to do that because we're not substituting something for du, we're substituting something for dx, so it'll be nice to have it in that form. When we do our substitutions, we'll leave that x for the moment. We're replacing that whole thing with u, so u to the 5th, and then we're replacing the dx with this. So we'll have du over 2x. Simplify this. X over x will cancel. Pull that 1/2 out front, so we have 1/2 integral u to the 5th du. When you're doing these, remember how nicely this works out. We do the substitution, we simplify, and we get something really easy to deal with. If you don't get something really easy to deal with, you're not doing it right. This one's easy to evaluate. U to the 5th becomes, what doesn't become, but we increase the exponent by 1, get u to the 6th, and then divide by the new exponent, so 1 over 6. And that gives us 1/12. U to the 6th power, but we know that u represents x squared minus 3. So 1/12 x squared minus 3 to the 6th power. If you want to write that as x squared minus 3 over 12, that's fine too. Any way you want to go. I'm probably going to make about 5 more of these with about 2 or 3 examples each, just to try and keep them shorter, but I do want to give you enough examples to sort of get the hang of this. So I'll see you several more times.